Hello everyone, today I'm going to talk about FedHiSyn, a hierarchical synchronous federated learning framework for resources and data heterogeneity. I'm Guanghao Li, and I will introduce our work. Federated learning is a distributed machine learning framework that utilizes edge devices to collaboratively train a global model while preserving data privacy. As shown in this figure, at each communication round of FL, the server first randomly selects several devices and sends the global model to the selected devices. Then, each selected device updates the global model with local data and uploads the updated model to the server. Finally, the server aggregates all uploaded local models to generate a new global model. These steps are repeated until the global model converges or predefined conditions are attained. By training model locally, FL stresses security and privacy problems, limited computing resources of edge nodes, and communication overhead. However, there are still some constraints in federated learning due to different user habits, heterogeneous data, heterogeneous resources, privacy, efficiency, security, communication, and so on. In this work, we mainly focus on heterogeneous data and heterogeneous resources. Heterogeneous data problem mainly refers to non-independent and identically distributed data on different devices, and the heterogeneous resources problem refers to a large number of devices of varying computing power. At present, the work on heterogeneous data is mainly divided into the following three aspects. The first is regularization, like FedDyn scaffold, which refers to adding a regularization term to the global optimization goal of federated learning, so that the optimization goal on each device is closer to the global optimization goal. This approach is difficult to deal with large-scale federated learning systems. The second is selecting devices. Selecting those devices with better data distribution to mitigate the impact of non-ID data. For example, ORT, favor CMFL, but selecting devices may ignore valuable data in some devices that are not selected. The last aspect is personalization. It means that each device has its own model, including FedRep and others. However, this method makes it difficult to select an initialization model for new devices. Works on federated learning heterogeneous resources mainly focus on synchronous and asynchronous aspects. Synchronous federated learning mainly refers to that all devices send update-wise to the server at the same time, such as FedCS, FedMCS. However, in synchronous federated learning, there is a problem that the device with weak computing power need other devices to wait it for a long time. In asynchronous federated learning, when the device finishes local updates and sends them to the server without waiting for other devices, such such as FedHiSyn, ASO Fed. However, asynchronous federated learning will cause frequent communication between the server and the devices, which will lead to the crash of the server. We make 3 different experiments. Through the first experiment, we found that the model trained through communication between devices will be more accurate than the model trained on individual devices separately, and the communication according to the ring topology will have a better effect than random communication. This is because communication makes weights carry more information from different devices. In the second experiment, we observed in a ring topology, the model accuracy can be effectively improved by organizing the communication between devices in a ring topology, wherein devices are ordered ascendingly or descendingly based on their local training time. In the third experiment, we observed clustering the devices with heterogeneous resources into different classes based on the duration of local training can accelerate the training but may lower the model accuracy. So, can we use communication between devices to help federated learning training? Now, we consider an edge computing system with a server and C devices. In each round, only part of all devices are selected for each round of training. Our final optimization goal is to minimize the loss function f of the global model. Stochastic gradient descent was performed on each device, while the server aggregates the received weights according to the Formula 3. The framework of FedHiSyn is shown in this figure. FedHiSyn mainly consists of 3 parts, including device clustering, local training of devices, and weights aggregation on the server. Clustering basically means that several are divided into different categories based on the computing power of each device. Generally, the categories include both the communication time and the local computing time of each device. But for simplicity, we will assume that all devices only have the same communication time. Therefore, only the local computation time of the device needs to be considered. After clustering devices of the same category form a ring topology according to training time. If devices receives a model sent by another device or the server, the weights are updated according to the first formula. Otherwise, the weights are updated according to the second formula. When the local update is complete, the updated weights are sent to the next device in the topology. Repeat the process until the communication time is over. The weight aggregation process is similar to the traditional federated learning, where the weights of each device are collected by the server. However, the weights collected in FedHiSyn will be trained by multiple devices of different categories. So the aggregation process needs to be based on the average calculation power of different categories as the aggregation weight standard. We evaluate the proposed framework based on MNIST, eMNIST, CIFAR-10, and CIFAR-100 datasets. Experimental results show that FedHiSyn outperforms 6 baseline methods, including FedAverage, Scaffold, and FedIt, in terms of training accuracy and efficiency. We have only shown part of the result here. First, data distribution across devices becomes more non-ID as we go from ID to directly 0.3. Increasing the non-ID level also results in greater communication saving in FedHiSyn. Second, the more difficult the work FedHiSyn has to do, the more significantly its performance improves over FedAverage. When the task is more complex, FedHiSyn can still train a model with higher accuracy by using the information transferred between devices. When the proportion of devices participating in training is small, the communication between devices can still be used to help train higher accuracy models. As shown in figure, when the number of clusters is set as 1, 10, 20, 30, 40, and 50, respectively, the final model accuracy of FedHiSyn first increases and then decreases, and the highest accuracy is obtained when the number of classes is set at 10. This verifies the motivation that if the number of clustered classes is too small, it is difficult for each class to complete multiple rounds of communication, resulting in a decrease in the efficiency of device communication and a higher accuracy. The greater the H is, the greater the degree of resources heterogeneity, as shown in the second figure. When H is set at 2, 4, 10, and 20, respectively, the accuracies of FedAverage model show an obvious downward trend on the two datasets, while those of FedHiSyn are considerably improved. It can be attributed to that as the degree of resource heterogeneity increases, devices with more computing power have more opportunities to communication with other devices before sending updates to the server in each round. At last, we design and implement a new tiered FL framework named FedHiSyn. FedHiSyn combines the centralized Federated Learning framework and the decentralized Federated Learning framework. FedHiSyn also utilized the communication among devices to reduce the communication load of the server and mitigate the impact of non-ID data. We plot a rigorous theoretical analysis of our proposed methods for strong convex objectives. We also evaluate FedHiSyn extensively on 4 datasets, and the experimental results show that FedHiSyn has better test accuracy and lower communication cost compared with 6 baselines. And that's our reference. That's all. Thanks for your listening.